which is not matching with experiment. And then you try to figure out that, okay, what were the problems in our assumption? How can we rectify our assumption so that we develop a better model? So this is how nuclear physics develops, okay? So it's a very phenomena-driven subject, and you do not have one model which can describe all of the nuclear phenomena. You have different type of models describing different type of things really, really well. So UPSC का जो syllabus है, ये nuclear physics के केस में थोड़ा सा I would say कि थोड़ा सा high level पे इसलिए है because when you look at the syllabus of quantum mechanics, in quantum mechanics the simplest type of potential problems have been handled. The potential problems in quantum mechanics are not at all very, very difficult. But because we are studying nuclear physics, these are the actual things which are happening in nature, so the problems are more difficult, okay? So the syllabus is very, very well defined. It's a very good syllabus. I will not say that it is a comprehensive syllabus. Of course, it cannot be a comprehensive syllabus, but it covers so many different domains of nuclear physics that it is very close to a comprehensive syllabus. So it should be given a lot of time. That as much time you give for quantum mechanics when you study, in fact, you should give more time for nuclear and particle physics to appreciate the subject in detail, what is happening. You simply cannot skip through subject. You simply cannot hope that कुछ formula याद रख लेते हैं and उससे हमारा काम चल जाएगा. If that is the plan, then it's not going to work really well during examination. And the reason I'm emphasizing upon कि याद से 10 साल पहले चल जाता, but आप पिछले 4-5 साल का question देखो, and you will find that in last 4-5 years, the type of questions they are asking, they have become more innovative. They are not asking those very simple traditional questions. They have become, at least few questions are more innovative, which will check your knowledge of physics, not just the formula itself, okay? So look at the syllabus. Syllabus is very well defined. It starts with basic nuclear properties. Okay. After Rutherford experiment, we got to know about nuclei. But then we want to know more about that nuclei. That what is the size of the nuclei? What is the binding energy of the nuclei? What is the angular momentum? What about parity? What about magnetic moment? Does it possess magnetic moment? Even though quadrupole moment is not mentioned in your syllabus, but quadrupole moment is also a very important parameter that tells you that if the charge distribution is uniform or if it is not uniform. So when quadrupole moment is a very important parameter which one should know here, right? So this is the first part of the syllabus, and you do expect some questions at least in that compulsory question number 5 जो है, यहाँ से आपके questions आएंगे. Then I can club first, second topic and fourth topic together, but I have simply described this syllabus as it is given. So the first model about nucleus, that some of these properties which you have just learnt here, not all of them, for example, particularly this property of binding energy. And for that, the first model you learn is called liquid drop model, where you assume nuclei as a again liquid, and then you look at the interaction. I do not know at all that nucleons के बीच में किस type का potential है, किस type का force है. I'm trying to do some estimation. I'm trying to imagine that चलो ठीक है, let's assume them to be a liquid, then think about nucleon which are inside, then think about the nucleon which are on the surface. The nucleon के बीच में एक तो मुझे पता है that जो protons हैं उनके बीच में एक repulsion होगा, so something is happening there. And then you try to further develop this model by looking into experimental data, and you come across many other parameters. So that liquid drop model becomes semi-empirical mass formula, and from semi-empirical mass formula you find mass parabolas, that for a given A, what all the isotopes can exist and which will be the most stable isotope. तो ये part हमको पढ़ना पड़ेगा. ये conceptually बहुत rich subject है. ये आपको देख के लगेगा कि बड़ा simple सा है, but ये conceptually इतना rich है that even that very simplistic model where I assume nuclei to be a liquid drop, I can actually explain that why neutron stars can exist. I will not go into that here, but if you go extend this idea, and then you will realize that even this simple model can explain that a neutron star can be a stable structure somewhere in this universe. But then we go into more details about the nature of potential which exists inside nucleus, right? This was very clear to scientists when nucleus was discovered. Even then it was very clear that clearly there is some other force which is making the nuclei stable, because otherwise you have a proton-proton repulsion, and that proton-proton repulsion should not make nuclei stable. So there must be some other forces which exist there, and those forces should have their own potential function, and we want to know what that potential function is and what is the nature of this force. So the simplest model they thought of, a stable simplest model, is Deuteron. It has one neutron, it has one proton, and then you solve Deuteron problem and you make lot of assumptions. Not all of those assumptions are correct, but despite making lot of those assumptions, while some being not correct, you actually find some remarkable things about the nature of nuclear force. For example, you know that it is a short range force. You know that the potential well due to nuclear force is much, much more than, let's say, electromagnetic repulsion also. You also know that it is a non-central force. Even though you start with assuming to be a central force, there are certain problems which will force you to rethink, and you'll realize that it is a non-central force. You also will know that it is not dependent upon charge, but dependent upon spin. There is a spin dependence here. So with lot of assumptions, you still can get some correct information about nature of strong nuclear force. And then the first well-developed theory of that strong nuclear force was provided by a scientist named Yukawa, and Yukawa was the one who proposed that model where fundamental particles exchange some particles, and as a result of that exchange, fundamental forces exist. So Yukawa proposed exchange between protons and neutrons, and the exchange is happening of pi mesons. Now we know that there is a more fundamental interaction than strong nuclear force, and that more fundamental interaction exists inside proton itself or exists inside neutron itself, and that is between quarks. So Yukawa ka jo exchange model hai, that has been retained, but rather than happening between proton and neutron, now we will say that it is happening actually between quarks with help of gluons. So now you jump from nuclear physics to particle physics. So in a way, nuclear physics started after developing quantum mechanics and atomic and molecular physics, but it led to genesis of particle physics. That you can think that from nuclear physics you have particle physics, that where you learn about fundamental particles and fundamental interactions and what are the nature of those fundamental interactions and all of that, and that part is something which you go into particle physics. But starting point of that is this very famous theory, Meson theory of nuclear forces. Okay. But semi-empirical mass formula has lot of limitations. So we come across that the same way there is an electronic configuration of electrons inside atom, there is a nucleonic configuration of protons and neutrons. And some of those nucleonic configurations are very stable compared to other, and there is a very good reason behind it, and all of that is provided by shell model. So shell model is very successful in some of the things, but not successful in some other things. For example, shell model will not help you in estimating binding energy, but it can help you in many other things really, really well. The biggest shock which occurred to physicists in 20th century was this next line which is given in your syllabus. Think of the shocks which have occurred in physics. Newton developed his ideas late 17th century. For 200 years, more or less, his ideas are correct. Of course, Lagrange adds his own method, Hamiltonian adds his own method, but more or less, his ideas are the guiding light. Okay. Then we come across this entire duality of light and fact that light is particle as well as wave. And then suddenly you have genesis of quantum mechanics. First shock, that the laws of physics at the very basic level, they are very, very different from laws of physics at very large scale. Second shock was given by Einstein again, that when he says that when things are traveling with very, very high speed, then you find some weird things which you cannot explain if you restrict yourself into your day-to-day life frame. So objects which are moving very fast, time will appear to be different for them. So it appears different from all different observers. The only thing is that at very small velocity, it does not make a lot of difference. But at very high velocity, that difference cannot be neglected. So that is the second shock, that space and time, they are not independent of each other. They are very much dependent of each other. So before that, before Einstein, everybody thought the time must be absolute. And Einstein challenged that. No, time is even time is not absolute. So similarly, there was one assumption which was true or which was considered de facto correct by all scientists throughout the time, that nature will not prefer any type of coordinate inversion. So if my laws of physics are happening in my right-handed coordinate system in one way, then we can also immediately write laws of physics in left-handed coordinate system. Or we use a better word for it, parity. That parity must be conserved in all type of interactions. Wherever interactions are happening, parity must be conserved. So if my law of physics is valid, if I'm writing one law of physics in my right-handed coordinate system, then accordingly I can write that in left-handed coordinate system. And this was a shock, that when we find that there is an interaction where that parity is violated. And that led to discovery of weak interaction, and that occurred with help of more and more study about beta decay. Even though beta decay was discovered much earlier, like Madame Curie at that point of time, so like some 30-40 years ago people knew about beta decay, but the fact that parity gets violated in beta decay, that was a shock, and that forced you to develop a fourth fundamental interaction, which we call weak interaction. So beautiful topic, again conceptually very rich. Then based on these ideas which you have developed, that the same way energy is quantized in atoms, energy is also quantized in nuclei. And the same way a particular atom or a particular molecule can only emit a specific frequency or can only absorb a specific frequency, same also holds true for nuclei. That nuclei also has its energy quantized, and as a result, only a very specific electromagnetic frequency can be absorbed or it can be emitted. Right. So this was confirmed with help of gamma decay. But with help of gamma decay, we developed more spectroscopic technique. The most famous one is Morse-Bauer spectroscopy. That now you become capable of answering certain questions which were not possible from atomic spectroscopy or molecular spectroscopy, which you have studied. Because Morse-Bauer spectroscopy allows you to look at the properties which are being governed at the level of nuclei, right? And this is the easiest part. This is the easiest part, Q value of nuclear reaction, fission and fusion, energy production in stars, nuclear reactor. ये सबसे easy part है, ये आपने 11-12 में भी पढ़ा है. But इसके अलावा ये कुछ भी, of course आपने radioactivity पढ़ा है 11-12 में, but radioactivity का आपने at max law पढ़ा है. That what is the law of radioactivity? You have not actually studied the theories behind radioactivity. And then from nuclear physics, that subject which emerges out of nuclear physics, particle physics, one of the most fundamental subjects in physics, that now you become interested in answering certain type of questions. One of the question is that what are the fundamental building blocks of the universe? That जो elementary particles as they are called, what are they? First, those elementary particles, what type of property they exhibit? Based on those properties, can we group them together? That I have one group of particle which has this property, another group of particle which has this property. And then turns out that yes, you can, and there are many ways to do that grouping. The most fundamental one you must have learned is Fermi-Dirac statistics versus Bose-Einstein statistics. That you have group of particles called fermions, and you have group of particles called bosons. But of course, there are many other ways to do that. So that is the first thing. That how do we classify them? Second thing, how do they interact? So then we ask question that if there were only particles and those particles had no interaction, then this universe would have been boring place. You and I would not have been there. The fact that quarks can come together and make a neutron and proton, and then neutron, proton, electrons can come together and make an atom and molecule and matter, and as a result all of us are here. So if you only have particles but no attractive or repulsive forces, then you do not have matter at all. You do not have anything in this universe. So we ask a question, what are those fundamental forces which bring these elementary particles together or which causes them to be repelled? And then we find that there are three fundamental forces which exist at very, very small scale. Now we know that there are four, but in particle physics we do not bother about gravitational force at all. The theory We do have a grand theory for particle physics, and that is called standard model. But the standard model of particle physics cannot account for gravitational force. For that, you have to go into Einstein's general theory of relativity. Okay. So you learn about fundamental interactions, and then you immediately see that in your even classical physics, you learnt about certain type of conservations. You learnt about momentum conservation, angular momentum conservation. By the way, have you guys studied that what are the fundamental reasons behind those conservation laws? That why is energy conserved, or why is momentum conserved, or why is angular momentum conserved? ये पढ़ा है आपने? I can only ask this question from you because you seem to have physics as a background. So if you have done BTech, then of course नहीं पढ़ा होगा. The Noether theorem पढ़ा था आपने college में? Noether theorem, one of the greatest discovery of 20th century has been that Noether, not as popular as Newton or Einstein, but her contribution is remarkable. It was Noether who proved that nature has certain symmetry, and whenever you have a symmetry, it brings a law of conservation. So for example, if I am doing something here versus I am doing something there, if I am doing same thing here, then I will have the same consequence as if I do there. So there is a translational symmetry in nature which leads to what is called conservation of linear momentum. And then similarly, if I rotate my coordinate system, so if I do something here, but the fact that universe is isotropic, that leads to conservation of angular momentum. And then also there is a time symmetry, that if I do something here, and if same thing happened in past, same thing is also going to happen in future. So there is a time symmetry also, and that leads to conservation of energy. So why Noether theorem is a very, very important idea? Because whenever you find a symmetry in nature, you find a conservation law, and vice versa. Whenever you find a conservation law, then you see that what type of symmetry leads to that conservation law. So ये UPSC preparation में आपको नहीं पढ़ना है. And I'm simply highlighting that there is a deep underlying theorem which explains conservation laws. So in particle physics, you learn about basic conservation laws. We all know momentum, energy, angular momentum, charge, mass, all of that. We know that. But in particle physics, you find more conservation laws. That there is something called baryon number, which must be conserved. There is something called lepton number, which must be conserved. There is something called CP or CPT that must be conserved. Strangeness is conserved in strong interactions and electromagnetic interaction, but in weak interaction, it seems to be violated. Parity, which I mentioned earlier, is conserved in strong interaction and electromagnetic interaction, but in weak interaction, it seems to be violated. So you learn about conservation laws, that what type of parameters are conserved in which type of fundamental interactions. And we particularly become very interested in answering two questions. First, what are the conservation laws which are true for all three? And second, what are the conservation laws which is only true for, let's say, which is not true for one of that? And the reason why we are interested in second question, because then we can answer, if I look at a particular reaction, I have a reaction given to me, it's a nuclear reaction. Elementary particles are reacting together. I want to know that which fundamental force became responsible for that particular reaction. So, ये conservation laws, और कौन से conservation laws कहाँ पे valid हैं, this allows you to determine that what type of fundamental interaction has occurred. And then particle physics goes into a very deep topic, and that deep topic is that, look, all of these fundamental forces which you are looking at right now, which we can see and we can experience and we can do experiments, at very high energy, they all were one. So when universe started, you did not have weak interaction and strong interaction and electromagnetic interaction. You had one. And that one can explain everything, right? So the same way we were able to combine electricity and magnetism in one theory, and we call that electromagnetic theory. As of now, scientists have been experimentally able to, like we have a theory and we have experimental confirmation that electromagnetic force and weak force, this can be combined into one theory that is called electro-weak force. We also have a theory to combine strong force here, but to do the experiment, we need much, much more energy, which is not possible right now. right? So a theory which can combine these three fundamental forces, strong, weak and electromagnetic, I call such theories grand unified theories. And the biggest problem in physics, the biggest, not one of the biggest problem in physics is that we have two beautiful theories in physics. First is called quantum mechanics and second is called general theory of relativity. And quantum mechanics seems to explain nature at very, very smaller scale so well. And general theory of relativity seems to explain nature at very large scale so well. But any effort to combine them into one theory seems to be futile. That we do not seem to find a theory which can combine these two into one. And that's a problem. That's a huge, huge challenge. You can ask a question that why do we need to combine it? Because in scientific method, I can easily accept the fact that nature at very large scale is guided by general theory of relativity, small scale guided by quantum mechanics. So why do I need to combine? So we need to combine to explain singularity. सबने बिग बैंग पढ़ा है, सेंटर ऑफ ब्लैक होल पढ़ा है, तो अभी अगर आप जनरल थ्योरी डिस्क्राइब करोगे तो जनरल थ्योरी के हिसाब से जो सेंटर ऑफ ब्लैक होल है उसका इनफाइनाइट डेंसिटी है. अब लोग इन्फिनिटी लुक्स ब्यूटीफुल इन मैथ्स बट नॉट इन फिजिक्स. फिजिसिस्ट विल नॉट एक्सेप्ट दैट देयर इज अ लिटरल इनफाइनाइट डेंसिटी एट द सेंटर ऑफ ब्लैक होल. सो व्हाट वी विल से दैट वी डू नॉट नो. We do not have a theory. हमारा जो notion of space and time है that breaks down when we try to explain center of black hole. So theory which can combine both quantum mechanics and general theory into one, we can call that quantum theory of gravity or theory of everything as it is called. So you, in the same topic, you have to have some very basic ideas about unification of forces. So you do not have to go into theory of everything. For example, that will include learning about string theory and quantum loop gravity. तो ये सब बिल्कुल नहीं आपको जानना है. As a theory भी नहीं जानना है. Maths तो छोड़ ही दो. But you have to know basic ideas about grand unified theories. That जो electroweak theory को हम strong से combine करेंगे, वो आपको पता होना चाहिए कि उसको लेके जो existing theoretical framework है वो क्या है. Without going into complicated maths, you have to have a brief theoretical understanding of that. And last but not the least, one of the nature's most mysterious particles is neutrinos. And what is happening regarding physics of neutrinos, what we know about neutrinos right now, what we want to know in future, you need to study that also as a topic, right? So this is a very, very important topic in section B. All candidates should aspire that in paper 2 you are solving 3 questions in section A and 2 questions in section B. Right? Of course, question number 1 and 5 are compulsory. And one of the biggest problem which I do think in physics optional students do is that section B का जो दूसरा part है, solid state physics, devices, electronics, वो बहुत सारे लोग बहुत ठीक से करते नहीं हैं. और उसका limitation फिर ये हो जाता है कि अब आपके पास ऑप्शन नहीं है कि अगर आपको न्यूक्लियर का कुछ सिंपल सा पूछा यूपीएससी ने फिर तो आप कर लोगे, आपके 5 क्वेश्चन हो गए, पर थोड़ा सा भी मुश्किल कर दिया अब आपके पास ऑप्शन ही नहीं है. तो ये एक पेपर 2 में बहुत बार थोड़ा सा कम स्कोर जो रह जाता है लोगों का इसलिए होता है. बट इवन देन आई मस्ट टेल यू दैट यूपीएससी कभी बहुत रेयरली होगा कि सारे के सारे क्वेश्चन ही न्यूक्लियर पार्टिकल के बहुत मुश्किल हो. इतना तो लीवे हमेशा देते हैं. मान लो हो सकता है कि आपको 15 नंबर का नहीं आता हो, 10 नंबर का नहीं आता हो, बट यू विल गेट मोस्ट ऑफ दैट करेक्ट. But we should try to complete the syllabus. The main point here is that we should try to complete the syllabus because only then we become better at filtering that what we should attempt and what we should not attempt. Okay. The book which I recommend, I have 2 books here. That is why I brought this book. So one of the most beautiful book written on this topic is by Kenneth S. Crane. This book is Introductory Nuclear Physics. So for undergraduate program, this is a very, very good book. But if you're preparing for UPSC, I will recommend this book. And the reason I will recommend, so this is Nuclear Physics by DC Tayal. And the reason I'm recommending this book here is because I have seen many questions asked by UPSC which are given as a solved problem in DC Tayal, right? तो एक तो यही कारण है. दूसरा ये है कि कुछ टॉपिक्स बहुत इलेबोरेट तरीके से दे रखा है डीसी तयाल में, जैसे जो सेमी इंपिरिकल मास फार्मूला है वो आपको बहुत डिटेल में यहाँ पे मिलेगा, nth क्रेन में उतना डिटेल में आपको नहीं मिलेगा, राइट. सो if you have to buy one. Don't be scared of looking at the thickness of this book. Remember that you have to read very specific chapters, and even within those specific chapters you have to read very specific sections. So you do not have to read each and everything. Okay. How I have divided this topic? I have divided this topic into 5 tutorials given the syllabus, which is, let me show you those 5 tutorials briefly, and then I will start the discussion. The first tutorial includes 2 topics. That first topic which you looked at, basic properties of nucleus, and second, the first model, semi-empirical mass formula. And you'll see that good number of questions. Then the second topic includes Deuteron and salient features of nuclear forces, the Deuteron problem as well as Meson theory of nuclear forces. The third tutorial includes shell model, right? Third tutorial only includes shell model. This only includes shell model. Radioactivity and nuclear reactions, I have included that into fourth tutorial. So fourth tutorial includes everything about radioactivity as well as nuclear reactions, reactors and everything. And fifth tutorial is dedicated to particle physics, right? So यहाँ पे एक चैलेंज ये है न्यूक्लियर पार्टिकल फिजिक्स में कि ये क्वांटम मैकेनिक्स से ज़्यादा बड़ा टॉपिक है. क्वांटम मैकेनिक्स में बहुत ही स्पेसिफिक पोटेंशियल्स आपको पढ़ने हैं, विच मेक्स दैट सिंपल. ये ज़्यादा बड़ा है, एज अ रिजल्ट यूपीएससी के पास ऑप्शन ज़्यादा हैं कि वो कौन से टॉपिक से क्वेश्चन पूछ सकती है. एंड एज अ रिजल्ट, फॉर एग्जाम्पल, आई हैव डिवाइडेड दैट इनटू 5 ट्यूटोरियल्स एंड लुक एट द डिस्ट्रीब्यूशन ऑफ मार्क्स फ्रॉम दिस 5 ट्यूटोरियल्स. Tutorial 1, that basic side semi-empirical mass formula, 95 marks. Tutorial 2, the Deuteron problem, salient feature of nuclear forces, 35 marks in 3 years. Tutorial 3, shell model, only one question in last 3 years. Not for a moment you should think that this is not an important topic. Remember that I have only included shell model, just one topic in tutorial 3. So there will be questions. Jaise is SAL, I'm definitely expecting some question on shell model this year. Then tutorial 4, that radioactivity and Q value and everything in tutorial 4. And finally, tutorial 5 of particle physics, right? So UPSC has a lot of leeways and they can ask questions from many, many things. So let's start our discussion. Let's start our discussion with some really fundamental questions. This include last 3 years, so 2022, 23 and 24. The first question is that write down Weizsäcker semi-empirical mass formula, explain each term. That's a 10 marker question. And second is explain why 238, uranium 238 is alpha emitter or not a beta emitter. So it should be very clear that using this you have to explain this. Using semi-empirical mass formula you have to explain this particular thing. This is a question which should make every candidate very, very happy, because you learn that in your paper 1. जो रदरफोर्ड स्कैटरिंग है वो क्लासिकल मैकेनिक्स का पार्ट है, बट यहाँ पे 20 नंबर का पूछा है न्यूक्लियर में. इवन दो मेंशन नहीं है सिलेबस में, बट द फैक्ट दैट यू आर सपोज टू नो बेसिक न्यूक्लियर प्रॉपर्टीज, एंड बेसिक न्यूक्लियर प्रॉपर्टीज विल स्टार्ट विथ द डिस्कवरी ऑफ न्यूक्लियस इटसेल्फ, एंड दैट हैपेंस आफ्टर Rutherford experiment. So such type of question should make you very happy that you study a topic at one place and you are getting benefited in another topic. Third is assuming nucleus as a cubical box of length equal to nuclear diameter of this, calculate the kinetic energy of highest level occupied by nucleon of iron 56 nucleus. This is the direct application of quantum mechanics which you have studied in your section A. Okay, so let's look at the solutions of these topics. Not a very good scan. So Weizsäcker semi-empirical mass formula, which emerges out of this very simplistic model, which is called liquid drop model, that essentially approximates binding energy of a nucleus and connects with mass of nucleus. So starting with the ideas of provided by Einstein, A is equal to mc square, that in a bound state, that mass is going to be little less, and that is essentially the binding energy of the nucleus. So this part is very obvious, that mass of a nucleus which has Z proton and A minus Z neutrons, that is mass of proton, mass of neutron, but because they are in a bound state, and that bound state has an energy associated with it, and we call that energy binding energy associated with particular number of protons and neutron. अब सेमी एम्पिरिकल मास फार्मूला का जो ऑब्जेक्टिव है वो इसको एस्टिमेट करना है, दैट ये जो बाइंडिंग एनर्जी है वो क्या है, right? So when I put this binding energy formula as per semi-empirical mass formula, that becomes my complete Weizsäcker semi-empirical mass formula. So again, those who have studied nuclear physics, they will remember this, that semi-empirical mass formula, it starts with liquid drop model, and then it keeps on adding terms. So for example, it says that imagine all of the nucleon as, let's say, you have molecules inside a liquid. Then you start with first assumption that every nucleon is contributing equal value to the binding energy. That is my assumption, right? So this energy is going to be proportional to the entire volume of the nucleus itself. So this is called volume term, that my binding energy is proportional to A. But then you also see that, look, in the liquid you have certain atoms which are on the surface, and as a result we have a phenomena called surface tension. Surface tension padha humne, that inside you have same molecules but outside you have some other particle, right? So as a result, the binding energy little bit reduces because of nucleons which are on the surface of nuclei. So you have surface term, and because volume is proportional to A, this is, and surface area is proportional to A to the power 2 by 3. So you have surface term. But then you also realize that, look, I have protons here, and those protons have a repulsion, and that repulsion is also going to bring down that binding energy. So we have a Coulomb term, and Coulomb term is proportional to z minus 1 divided by A to the power 1 by 3. It's a very simple one-line derivation, that y z minus 1 A to the power 1 by 3. So this can be, for example, z minus 1 का तो simple कारण ये है that if I have z proton and I'm including 2 protons at one point of time, so it is nothing but z combination 2, which is z minus 1 divided by 2. Y A1 by 3, again this is just a one-line calculation can be shown. So this was our initial liquid drop model. When the model was developed, these were the 3 parameters. Okay. So people then saw that हमारे पास एक्सपेरिमेंटल डेटा है बाइंडिंग एनर्जी का, अब इसको हम देखते हैं कि फिट बैठता है कि नहीं एक्सपेरिमेंटल डेटा में, एंड दे इमीडिएटली रियलाइज दैट ये फिट नहीं बैठ रहा, ठीक है. Then they saw that you have certain nuclei which have more number of neutrons compared to proton. So that we started thinking about that n is equal to z line, that is, let's say, my stability line. So as the number of neutrons are increasing, that is causing some sort of asymmetry. And then they tried to estimate that what will be the approximate value of that asymmetry energy. And again, this can be also shown. इस क्वेश्चन में आपको करने की जरूरत नहीं है, सिर्फ 10 नंबर का क्वेश्चन है, but it can be shown that that asymmetric energy will be proportional to A minus 2z whole square divided by A. Then people looked at कि now does this justify binding energy value, and turned out कि नहीं, अभी भी थोड़ा सा एक कमी रह गया है, that it was justifying binding energy for many of them, but then they found that those nuclei which have both even number of protons and even number of neutrons, they seem to have more stability. And it made sense based on Pauli exclusion principle, versus those who have even number of proton, odd number of neutron, or odd number of proton, even number of neutron, versus both proton and neutron having odd number. And that led to the last term, which is called pairing term, and that is often shown with delta. So this is the complete binding energy value, and you have to describe each and everything here. Volume term, I assume each nucleon contributes approximately equal to binding energy. My binding energy due to volume term is proportional to A. Nucleons on the surface are less tightly bound, that will reduce the binding energy proportional to A to the power 2 by 3. Coulomb term, that is the electromagnetic repulsion, that again will bring down that binding energy. Asymmetric term, that this n is equal to z line, equal number of neutrons and equal number of protons, but then you start finding a departure. The observed value is that you have more number of neutrons for heavier nuclei. इस पे भी UPSC ने पूछा है that why is it so? That why do we have more number of neutron versus why do we not have a scenario where we have more number of protons? Can you answer that question? It's a very simple question, that for most of the nuclei, it is either equal number of neutrons and protons, but when you go to larger values, you have more number of neutrons versus protons. What could be the reason? Start from first principle. First principle का क्या मतलब होता है? First principle का मतलब ये होता है कि हम किसी भी चीज़ को जो थ्रो कर रखा है, हम उसको स्क्रूटनाइज करते हैं, हम देखते हैं कि इसके पीछे जो अंडरलाइंग रीजन है वो क्या है. So I want to look at the stability of nuclei. न्यूक्लियाई के जो न्यूक्लियॉन्स हैं उनके बीच में क्लियरली हमको दिख रहा है कि एक अट्रैक्टिव फोर्स है. आई डू नॉट नो व्हाट दैट अट्रैक्टिव फोर्स इज, बट देयर इज अट्रैक्टिव फोर्स. बट आई नो फॉर अ फैक्ट देयर इज अ रिपल्सिव फोर्स बिटवीन प्रोटॉन्स. As nuclei become bigger and bigger, their size increases, right? So as this size increases, if I have more number of protons, then that repulsion of proton will start exceeding than attraction between proton, 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 neutron, or neutron, neutron. That also tells you, by the way, immediately that ये जो attractive force है nucleus के अंदर ये short range force है, कि ये एक रेंज के बाद ये ऑपरेट करना बंद कर जाता है. सो एज न्यूक्लियस बिकम्स बिगर एंड बिगर, टू कॉम्पेंसेट फॉर दैट एक्स्ट्रा इलेक्ट्रोमैग्नेटिक रिपल्शन विच इज हैपनिंग बिटवीन प्रोटॉन्स एंड प्रोटॉन्स, आई नीड टू हैव मोर नंबर ऑफ न्यूट्रॉन्स. ठीक है, बिकॉज न्यूट्रॉन्स के बीच में कोई इलेक्ट्रोमैग्नेटिक रिपल्शन नहीं होगा. बट इट कैन बी प्रूवन नाउ विथ हेल्प ऑफ क्वांटम मैकेनिक्स दैट न्यूक्लियाई एक नंबर के बाद एग्जिस्ट करेंगे ही नहीं, बिकॉज जो इलेक्ट्रोमैग्नेटिक रिपल्शन है इतना ज़्यादा हो जाएगा दैट न्यूक्लियाई इज नॉट गोइंग टू बी अवेलेबल एट ऑल. थिंक ऑफ ऑल ऑफ द नेचुरल एलिमेंट्स विच एग्जिस्ट. नेचुरल एलिमेंट्स कितने मिलते हैं नेचर में? आई थिंक सम 94 or 95 of them. The total elements in periodic table are 118, but I hope you guys know that most of them have been made into lab, right? So there is a reason why is it so, and even within those natural elements you find that for heavier elements many of them are radioactive, that they emit alpha or beta and they want to gain more stability. Okay, so anyways, there is a asymmetric term, that neutron proton imbalance, and excess neutron decreases the binding energy. This is an assumption, and based on that we develop this. And last but not the least, we find that even nuclei, they have more stability. Odd nuclei, they have very less stability, and this is completely experimental data. इसका कोई लॉजिक भी नहीं है. जैसे मैं अभी asymmetric term को फिर भी मैं logically justify कर सकता हूँ that why it is a minus 2z whole square by a, but ये बिल्कुल experimental data है that if you have even nuclei, which means that proton number is also even, neutron number is also even, then binding energy improves. If it is odd a nuclei, which means that I have either one of the nucleon is even, another is odd, then it does not, that pairing term does not contribute to anything. And if both of them are odd, then it reduces. Nuclei becomes less stable. So this is an experimental data, and people try to fit the experimental curve two other four terms which already have developed, and then they found that if we add this parameter, then it is matching with our experimental data. I will go back to what I started with, that nuclear physics is a lot phenomena driven model, that we do not have one model to explain each and everything. So now we have the complete term, and this is not a very good diagram. I would hope that in examination you will make a better diagram, that if I only include volume energy, then I find that flat. Remember, volume energy is proportional to A. When I include volume plus surface, then I find this curve. When I include volume plus surface plus Coulomb, then I find this curve. Volume plus surface plus asymmetric term, this curve. And then for some of them, that extra stability is that volume plus surface plus asymmetric plus pairing plus Coulomb, everything. And this is your final binding energy per nucleon versus A graph, right? Peak occurs at iron 56. So this is your first part of the question. Second part of the question भी बहुत interesting है. क्वेश्चन में देखो, सेकेंड पार्ट में दो सब पार्ट है. दैट यूरेनियम 238 इज एन अल्फा इमीटर बट नॉट अ बीटा इमीटर. ये कैसे करोगे? हाउ विल यू सॉल्व दिस? ये इतना आसान नहीं है जितना लग रहा है. द रीजन इतना आसान नहीं है बिकॉज आपको इसके लिए कुछ कुछ टर्म्स के, ये जो कॉन्स्टेंट्स थे उनमें कुछ कॉन्स्टेंट्स के वैल्यू आपको पता होने चाहिए, नॉट ऑल ऑफ देम. सो हाउ विल यू सॉल्व दिस? आपको दिखाना पड़ेगा कि आफ्टर बीटा डीके द बाइंडिंग एनर्जी इंप्रूव्स. सॉरी, आफ्टर बीटा डीके इन केस ऑफ यूरेनियम, अगर बीटा डीके हो रहा हो तो बाइंडिंग एनर्जी एक्चुअली में घट जाएगा, अल्फा डीके में बाइंडिंग एनर्जी इंप्रूव होगा. सो इफ आई प्रूव दैट, देन आई हैव प्रूव्ड इट. तो आई स्टार्ट विथ माई पेरेंट न्यूक्लियस बाइंडिंग एनर्जी एंड देन आई टॉक अबाउट डॉटर न्यूक्लियस बाइंडिंग एनर्जी. तो अगर बीटा डीके हो रहा हो, भाई द वे ये सारे पैरामीटर्स पता होने चाहिए. और ये जो पैरामीटर है ये इसमें गलत दे रखा है, ये आउटडेटेड बुक है अभी के हिसाब से. जो रिसेंट एक्सपेरिमेंटल डेटा है दैट, मतलब गलत नहीं दे रखा है, ये थोड़ा सा डिपार्चर है. इसमें जो वैल्यू दे रखा है ये थोड़ा सा पुराना वैल्यू है, ये बुक बहुत सालों से रिवाइज हुई नहीं है. अगर क्रेन आप पढ़ोगे तो वहां पे क्लियरली आपको दिख जाएगा, क्रेन इज अ मच मोर रिवाइज्ड बुक एंड दीज आर द एक्सपेरिमेंटली कंफर्म्ड वैल्यूज ऑफ दोस कांस्टेंट. जो वॉल्यूम टर्म का कांस्टेंट है वो ये है, सरफेस का कांस्टेंट ये है. सो यू हैव ऑल ऑफ दिस कांस्टेंट्स. अब इन कांस्टेंट्स को यूज करके आप देखोगे दैट इफ यू हैव बीटा डीके, यूरेनियम emitting a beta, and then you check that is binding energy improving or not improving. So beta decay produces an isobar. So isobar में जहां जहां पे A वाले टर्म है उसको तो हम इग्नोर कर देंगे बिकॉज A वाले टर्म का तो कोई कॉन्ट्रीब्यूशन होगा नहीं. आई ओनली नीड टू वरी अबाउट Z टर्म्स वेयर Z is involved. So I look at, for example, asymmetric term, I look at Coulomb term, and I look at pairing term. These three things I see and I realize that binding energy is not improving. So beta decay is not going to be possible. And I do the same calculation for alpha decay and I show that in alpha decay, for example, जो Coulomb term है वो significantly कम हो जाएगा हमारा. Remember Z is reducing. Alpha decay में जो pairing term है उस पर कोई impact नहीं पड़ेगा because helium alpha क्या है, 2 4 है. So 2 proton and 2 neutron are emitting. So pairing term पे फर्क नहीं पड़ रहा है, right? तो ये हम दिखाएंगे and we will show that this is feasible. तो बट इसके लिए if you do not know the constants, you do not remember the constant, it's going to be a difficult question to answer. एक और क्वेश्चन जो आप एक्सपेक्ट कर सकते हो इस पे वो ये है that यहाँ पे तो चलो यूरेनियम 238 का स्पेशल एग्जांपल लिया, but it can be proven using semi empirical mass formula that for any mass number which is more than 140 150 alpha decay will be a favorable pathway. So I do not have to think only about uranium 238. I simply have to, for such question, ये आपका एक homework है जो आप कर सकते हो. That imagine I have X, Z, A minus 4 plus alpha. ठीक है, आप इसका सेमी इंपेरिकल मास फार्मूला बाइंडिंग एनर्जी लिखना, इसका बाइंडिंग एनर्जी निकला. अल्फा का हमको पता होता है, अल्फा का डेटा आपको दे रखा होगा कि अल्फा का जो टोटल एनर्जी है वो क्या होगा, एंड फिर उसके बाद आप सब्ट्रैक्ट डेल्टा बी निकालोगे, और डेल्टा बी में जो मेरा डेल्टा जेड है दैट इज गोइंग टू बी 2, एंड जो मेरा डेल्टा ए है दैट इज गोइंग टू बी 4, एंड बेस्ड ऑन दैट आप कैलकुलेट करोगे, यू विल फाइंड एन इक्वेशन, एंड उस इक्वेशन का सॉल्यूशन तभी बढ़िया होगा व्हेन ए विल बी ग्रेटर दैन सम 120 और 150, आई डोंट रिमेंबर द एग्जैक्ट वैल्यू बट समथिंग लाइक दैट. सो ये इस टाइप का भी क्वेश्चन आ सकता है फ्रॉम सेमी एम्पिरिकल मास फार्मूला. सेकेंड जो क्वेश्चन था रदरफोर्ड स्कैटरिंग वाला, ये तो बहुत ही स्टैंडर्ड क्वेश्चन है और इसका मैंने कुछ ज़्यादा कॉम्प्रिहेंसिव सोल्यूशन लिखा है. आपको एग्जाम में पूरा इतना कॉम्प्रिहेंसिव करने की ज़रूरत नहीं है, बट दिस कैन बी फॉर एग्जाम्पल पीपल हु हैव नॉट स्टडीड दिस टॉपिक, यू कैन थिंक ऑफ दिस एज अ स्टैंडर्ड नोट्स, दैट इससे ज़्यादा और रदरफोर्ड स्कैटरिंग में जानने की और ज़रूरत नहीं है. एक दो चीज़ें और क्वेश्चन आ सकता है, जैसे पूरा देखो रदरफोर्ड स्कैटरिंग है क्या, कौन कौन से डायग्राम्स हमको बनाने चाहिए. I take a sample, it's a radioactive sample such as radium which emits alpha. I use collimator. If I want to add more, I use collimator here. Collimator का पर्पस क्या होता है, डायरेक्ट करना, जो मेरा पूरा अल्फा रेडिएशन है उसको डायरेक्ट करना. Then after that I bombard it on a very thin gold foil which is about 1 micron meter thick, and I see that what is happening to that alpha particle. How do I see that? I have a fluorescent screen. That fluorescent screen, when alpha particle hits that, it releases a flash of light, and then with help of a telescope I actually calculate that how much of that scattering has actually happened. This is my experimental observation. This is the experimental setup. And after this experimental setup, what did Rutherford found? That most of those alpha particles are crossing undisturbed. Some of them are getting scattered by various angle, but some of them are also getting back scattered, where the scattering is almost approximately 180 degree, right? So this is the phenomena, which means that most of the atom is empty, but you do have a very heavy object at the center of the atom, and I can think of this as a positively charged, because alpha particle 2, 4, that is getting repelled by that positive charged nuclei. So Rutherford made certain assumptions. The first assumption was that जो interaction है वो सिर्फ और सिर्फ Coulomb potential है, there is no other interaction. Second assumption is कि जो scattering है वो elastic है, that there is no loss of energy in this entire scattering. The data, now the data, when he discovered, he came to a realization that most of the atom is empty, as due to the fact that most of the alpha particles are crossing undisturbed. Small fractions are scattered, some are back scattered, and that leads to the assumption that there is a positively charged atomic nuclei. That is the conclusion of this experiment. And ये जो सारे calculations हैं, we are doing that in center of mass frame of reference. This is again not a very good picture. I can make better diagram than this, but this is not a very good picture. So imagine this. जब भी हमको scattering करना हो, we look at a very important parameter which is called impact parameter. That this is my line of sight. My experiment is happening. This is my line of sight. I have a center of force. ये मेरा center of force है. इस center of force से एक जो particle है, वो कितने height पे है? This parameter is called impact parameter. And as it is getting, we do not know what type of force. Now we know after experiment that it is a repulsive force. It is a Coulomb repulsion. So it is getting scattered. Okay? It is getting scattered due to this. तो ये जो पूरा scattered है, जैसे ये पूरे इस fraction में, ये b height पे, मान लो imagine करो that this is my line of sight, and I have this circular ring of impact parameter b, and width is db. So all of these particles, they're going to get scattered between this solid angle represented between omega and d omega, right? So that d sigma by d omega is called differential cross section, and पूरा Rutherford scattering में हमारा जो main part क्या होगा, that is d sigma by d omega को b के term में लिखना, and accordingly फिर देखना कि हमारा जो scattering theta है वो क्या है, ठीक है? So we will write everything. हमने impact parameter define किया. perpendicular distance between the center of force and the incident velocity, and we need to find the relation between B and scattering angle theta. Ab now we will go to the physical diagram. So ये डायग्राम आपको बनाना पड़ेगा, बाकी आपने बनाया हो ना बनाया हो फर्क नहीं पड़ता, बट ये डायग्राम आपको बनाना पड़ेगा. That this is my impact parameter, this is the closest approach which it reaches to. एक जो क्वेश्चन और पूछ सकती है, यूपीएससी पूछा भी है कि ये जो ट्रेजेक्ट्री है हाइपरबोलिक ट्रेजेक्ट्री है, ये जो दिख रहा है आपको, दिस ट्रेजेक्ट्री इज अ हाइपरबोला व्हिच कैन बी अगेन प्रूवन वेरी वेरी इजीली. राइट, दिस इज माय स्कैटरिंग, this is my force, center of force, Z2E, Z2 here is gold, and this is Z1E, which is my alpha particle. So I want to now use my three conservation laws: conservation of momentum, conservation of energy, and conservation of angular momentum. And using these three conservation laws, I will figure out the relationship between B and theta. So I'm not making any, I'm not doing even any quantum mechanics here. That was the beauty of this experiment, that even though we do know that such type of interactions we should only and only do with help of quantum mechanics, but even with those classical assumptions, Rutherford got a lot of things correct. So if this is my initial momentum Pi and this is my final momentum Pf, then I want to calculate what is that change in momentum, and that change in momentum can be written down in the theta form. So आप ऐसे देखो, this is Pi, this is Pf, and let's say this is the scattering angle theta, which I already have defined. Because mod Pi, mod Pf should be same here, assuming that जो ये scatter जिससे हुआ बहुत ही heavy है. So del P should be equal. So if this angle is phi and this angle, let's not use phi, let's use alpha, then 2 alpha plus theta should be pi. So alpha here is nothing but pi by 2 minus theta by 2, pi by 2 minus theta by 2. Now I use simple triangular law, that this delta p divided by this angle, which is nothing but theta, should be same as p divided by should be same as Pf divided by this angle, which is nothing but pi by 2 minus theta by 2. So I do that, del p by sine theta, p divided by sine pi by 2 minus theta by 2, this is cos theta by 2. Now sine theta can be written as 2 sine theta by 2 cos theta by 2. Remove cos theta by 2, I find del p is nothing but 2 pi sine theta by 2. So this is our first relationship which we have received from change in momentum. Okay. Second relationship which we are going to get, which by the way we can further connect this, that this change in momentum should be equal to the total impulse imparted by that electromagnetic repulsion. Electromagnetic repulsion can be easily written as Z1 Z2 by R square E square. ठीक है. अब जो पूरा ट्रेजेक्ट्री है जो मेरा फाई है, फाई इज इसेंशियली z एक्सिस, तो इसके कंपैरिजन में जो मेरा ट्रेजेक्ट्री है पूरा सिमेट्रिक है. सो जो फोर्स है दैट शुड बी f cos phi dt, and now I am getting some sort of relationship between cos phi by r square dt, but we do not know this relationship, कि how these things are connected. So I need more constant of motion. And what is another constant of motion? Second constant of motion is conservation of angular momentum. So my initial conservation of angular momentum is m v naught b when it was very far away from that nucleus. After interaction, the angular momentum is m r square. It's a point particle. Moment of inertia is m into r square, and angular velocity is d phi by d theta. So यहाँ से मुझे dt by r square के बीच में एक relationship मिल गया. So dt by r square cos phi जो था, I replace that and I find this. अब मेरा phi कहाँ से कहाँ तक vary करेगा? So if it is undisturbed, if it is crossing undisturbed, then that is pi minus theta by 2, and if it is getting backscattered, that is minus pi minus theta by 2. I do this and I find that del p in terms of theta is this. But I still do not know everything, because I still do not know. I still can eliminate few things. For example, we can use the conservation of energy now. So पहले तो del p 2p sin theta by 2 हमने निकाला ही था. हमने यहाँ से भी निकाल लिया del p. We equate that and we find a very nice relationship between b and theta. That z1 z2 e square by 4 pi epsilon naught 1 by 2 k cot theta by 2. All of this is constant. If I assume that all alpha particles are being released with same kinetic energy, then I can think even k as constant. So I find a very nice relation between b and theta. But I can further do one final trick we have, and that trick is that if my initial kinetic energy is half mv naught square, there was a continuous repulsion. So at the closest approach to the nuclei, all of the kinetic energy is going to become converted into potential energy. So I do that kinetic energy k, and if my closest approach is 1 by d naught, then these two things should be equal. So if I define my closest approach as d1, then I find this very nice relationship, and the entire impact parameter and scattering angle, I find this very nice simple relationship. B is equal to d naught by 2 cot theta by 2. And the last part now is that I have to, based on this relationship, I have to now calculate what is my differential scattering cross section. तो उसके लिए I will go back to our initial assumption that जो पूरा ये ring था 2 pi b db, all of that ring crossed into that solid angle 2 pi sin theta d theta. So this is my differential cross section, d sigma by d omega 2 pi b db divided by 2 pi sin theta d theta. So d sigma by d omega is nothing but b by sin theta db by d theta. And आप आराम से इसको करो, and ये आपका relationship मिल गया, d naught by 4 square 1 by sin 4 theta by 2. So जो मेरा differential scattering cross section है, that is proportional to cosec 4 theta by 2. And आप इसको plot कर सकते हो. This is going to be the plot, that as theta increases, the number of particles, that is the differential cross section, is going to decrease. तो ये complete answer, complete topic है. इसमें 2-3 टाइप के और क्वेश्चंस आ सकते हैं, जैसे हाइपरबोलिक ट्रेजेक्टरी पूछा जा सकता है, that prove that this trajectory is hyperbola. Rigid अगर sphere हो तो total cross section पूछा जा सकता है. That is a type of question which can be asked in paper 1, not here but in paper 1. If you want to reduce the number of pages here, then you can remove few diagrams. For example, आप इस diagram को हटा सकते हो, right? इस diagram को ideally नहीं हटाना चाहिए, but अगर आप इसको भी हटाना है तो इसको भी हटा सकते हो. But ये जो दो diagram मैंने बनाए हैं, this diagram and this diagram, these two diagrams must be made when you are doing the complete derivation of scattering cross section. Okay. Next one is very easy. ये कैसे करोगे? Again, I would want this. We will solve. We'll do this question later. Okay. Let's see this question. That by assuming the nucleus as a cubical box of length equal to nuclear diameter 10 to the power minus 12 centimeter, calculate the kinetic energy of the highest level occupied nucleon of iron 56 nucleus. How will we solve this? So, इसमें अगर आप बहुत ही precise अपने arguments में नहीं हो, you will not get any marks. Let me explain what do I mean by that. Iron has 56. So, let's look at everything. पहले तो we know that cubical box का energy क्या होता है? h square by 8 ml square, nx square plus ny square plus nz square. Those nx, ny and nz, they represent quantum states. We also know when you solve this, इस क्वेश्चन में आपको सॉल्व करने की जरूरत नहीं है. ये फॉर्मूला ऑल्दो कोई बहुत कॉम्प्लिकेटेड है नहीं, डेरिवेशन है. इफ यू नो द वन डायमेंशनल पोटेंशियल, उसी का ये 3D फॉर्म है. वन डायमेंशनल पोटेंशियल इज एच स्क्वायर बाई 8 ml square n square. This is n1 square plus n2 square plus n3 square. You also know when you solve this that these three should be positive integers. All three of them should be integers and they should be positive. Okay. अब यहाँ पे कुछ चीजें हमको पता है. हमको L दे रखा है 10 to the power minus 12 centimeter. Let's convert everything into SI unit. So 10 femtometer, 10 to the power minus 14 meter. m हमको प्रोटॉन हम एज्यूम कर लेते हैं, प्रोटॉन न्यूट्रॉन कुछ भी एज्यूम कर सकते हैं, इक्वल ऑलमोस्ट इक्वल मास है 1.67 मल्टीप्लाइड बाई 10 to the power minus 27 kg. अब लेकिन जो ट्रिक ये होगा कि आयरन में यू हैव 26 प्रोटॉन्स एंड 30 न्यूट्रॉन्स. ठीक है, ये हमारा स्ट्रक्चर है. This 26 protons and 30 neutrons, they must obey Pauli exclusion principle. ये Pauli exclusion principle हमको use करना पड़ेगा. But protons and neutrons themselves are distinguishable from each other. Like proton is not same as neutron. Those 26 protons are indistinguishable. Those 30 neutrons are indistinguishable. But protons, neutrons themselves are indistinguishable. Why this is important? Because I can have same quantum number nx, ny, nz, separate quantum number for protons and for neutrons. I do not have to take all 56 of them together. The reason I am saying that अब हम क्या करेंगे, अब आप ये देखोगे कि कौन कौन से possible solutions हैं, ये आपको टेबल बना के पूरा करना पड़ेगा. nx, ny, nz can be positive integer. Based on nx, ny, nz, I have ns square. That ns square is nothing but nx square plus ny square plus nz square. But I will also see the degeneracy level, that how many possible combinations of nx, ny, nz will lead to same n square. And remember, in every level I can have two nucleons. These are fermions. Fermions will follow Pauli exclusion principle. So in every energy state I can have two nucleons. So if I have quantum state 1 1 1, then n square is 3, but इसका degeneracy सिर्फ एक ही है. 1 1 1 को अगर हम कर भी दे कोई फर्क नहीं पड़ता. But look at 1 1 2. I can have 1 1 2. I can have 1 2 1, and I can have 2 1 1. So I have degeneracy level 3. So in that 3 degeneracy level, in every level I can have 2 nucleons. So 6 nucleons fit into my next state. Then the third high level is 1 2 2. इसका भी same idea. इसका भी degeneracy level is also 3. 6 can fit there also. Then 1 1 3, same 3, 6 can fit here also. 2 2 2, again only one degeneracy level. I can only have that. The degeneracy is only one. I can have 2. 1 2 3. Now this can be 6 degeneracy levels. 1 2 3, 1 3 2. Right? You know simple permutation and combination. So I have total. Now look at the cumulative number. This is separate for neutron. I can have that nx, ny, nz separate for neutron, and I can have that nx, ny, nz separate for proton. This is what I wanted to highlight. कि अगर आप 56 करके चलोगे तो आपको आगे जाना पड़ेगा. But 56 आप इसलिए नहीं करोगे because Pauli exclusion principle will separately be followed by neutron and proton. अब total calculate करो. I had 30. How many neutrons I had? 30. Yeah, I had 30 neutrons. The first 2 fit into first quantum state, then 6, so I have 2 plus 6, 8, 14, 20, 22, and this is 34. So I only need for 26 of them. So I need to go into that nx, ny, nz where 1 2 3 should be there. So for that my n square is 14. 1 square plus 2 square plus 3 square, and this is going to be now the maximum energy. Since protons, and I have mentioned that I will make this argument that since protons and neutrons are distinguishable, they occupy independent quantum states. We need to find maximum nx, ny, nz for neutrons, that is 15 spatial state, because every spatial state I have 2 neutrons possible as per Pauli exclusion principle. And for that 15, I get that maximum ns square is equal to going to be 14. And now I can fit my formula. My E is hs square, 8 mls square, ns square here is 14. I directly have converted that into electron volt. Do all of that, and this is going to be the answer, 28.7 MeV. And by the way, even though we made simplistic assumptions of a cubic model and everything, you still will find that this is very close to the experimental data, that it's not very far away, it's not exactly correct, but it's also not very, very far away. So this is remarkable about even starting with simple potentials and getting correct results very close to experiment. अब ये तो बहुत ही सिंपल क्वेश्चन है. नेक्स्ट, न्यूक्लियर डेंसिटी, एटॉमिक डेंसिटी, इसमें ज़्यादा कुछ इसमें कुछ टाइम स्पेंड करने का मतलब ही नहीं है. न्यूक्लियर डेंसिटी विल बी मास ऑफ प्रोटॉन बाय वॉल्यूम ऑफ न्यूक्लियस. ये आपका आएगा ऑर्डर ऑफ 10 to the power 17. एटॉमिक डेंसिटी में आई हैव अगेन इग्नोर्ड मास ऑफ इलेक्ट्रॉन. आई हैव मेंशन्ड दैट, इग्नोरिंग मास ऑफ इलेक्ट्रॉन. फर्क नहीं पड़ता, ज़्यादा कुछ फर्क पड़ेगा नहीं, but that will be 10 to the power 3 kg. And what is important, that the ratio is 10 to the power 14. And the question is that what can we infer from that? And we can infer that almost all of the atom is concentrated in a very tiny nucleus. Atoms are mostly empty space filled with electron cloud. That's it. That is the inference we made from here. So this is a very, very simple question. Okay, next question is, does the nucleus possess magnetic moment? Justify your answer. Define nuclear magneton and Bohr magneton. Calculate their values. बहुत simple question है. इतना simple question आ जाए तो again you should be very happy. Of course, nucleus possess magnetic moment, and the reason they possess magnetic moment because nucleus is composed of protons and neutrons. Now protons and neutrons, they both have this intrinsic property called spin angular momentum, and as a result they both will have that spin magnetic moment. Proton, apart from spin, the fact that it is a charged particle and is moving around, let's say it is moving around, it will also have a orbital angular momentum, and as a result nucleus will have total magnetic moment. So that is what I have mentioned. Protons have charge and have intrinsic angular momentum. Neutrons, though neutral, have spin and magnetic moment due to internal quark structure, right? And as a result, the total magnetic moment arises from the intrinsic spin of nucleons, which includes both proton and neutron, and orbital motion of proton. And we also know that this magnetic moment is quantized, very similar to how magnetic moment at the atomic level is quantized. Even at the nuclear level it is quantized, and it is measurable via certain experiments such as nuclear magnetic resonance. And बाकी तो बहुत ही आसान है. Bohr magneton, that is simply defined as EH cross by 2 Me. Me here is mass of electron. इसका ये value आएगा, अब करके देख लेना. And nuclear magneton, that is 2 MP. EH cross by 2 MP. P here is MP is mass of proton. इसका ये value आएगा. और आप दोनों का ratio निकालोगे तो ratio will be same as ratio of mass of proton and mass of electron. Mass of electron and mass of proton 1 by 1837. So this is a simple question. Should be happy looking at this question. The next question, again it is easy, but you have to be very careful while solving the differential equation. Question ये है, write semi empirical mass formula जो हमने ऊपर लिखा था. Calculate the atomic number Z of most stable nucleus for given mass number using the above formula. A3 and A4 का वैल्यू दे रखा है. तो ये देखो सेमी इंपिरिकल मास फार्मूला है. अब यहाँ पे आपको मास पैराबोला सॉल्व करना पड़ेगा. फ्रॉम सेमी इंपिरिकल मास फार्मूला यू स्टडी अ टॉपिक विच इज कॉल्ड मास पैराबोला. सो दिस इज माय टोटल कंप्लीट सेमी इंपिरिकल मास फार्मूला जो अभी हमने थोड़ी देर पहले लिखा था. एंड अगर आप ये पूरा अरेंज करोगे, इन सबको सिंप्लीफाई करोगे, you find something like this: Z, MP minus Mn, AMN, A1A, all of that. And this, we find that this is like a parabolic equation, alpha, beta, gamma and delta, where alpha, beta and gamma and delta can be written into this form. ये आप खुद से simple सा arithmetic है, वो आप करके देख सकते हो. And ये एक A के लिए है. अब एक A के लिए बहुत सारे Z possible हैं. I have to find that what is the most stable Z. So I need the minimum value of that parabola. I take del m by del z, A is equal to constant 0. यहाँ से मेरा z नॉट आ गया बीटा बाई 2 गामा. एंड बीटा हमने निकाला था कॉन्स्टेंट्स के फॉर्म में, गामा भी निकाला था हमने कांस्टेंट के फॉर्म में. ये हमारा वैल्यू है. यहाँ पे A2 और A3 दे रखा है, A4 A3 दे रखा है, A2 भी होगा. सो आइडियली उनको A2 भी देना चाहिए. बट पुट ऑल ऑफ दैट and you will find a ready-made formula that if A is given, then which Z will be the most stable. So this is a question which you can, this is one of the application of semi-empirical mass formula, that among all the isobars, which isobar is going to be the most stable. So that was the first tutorial. This is a fantastic question. If the nuclear force is charge independent and a neutron and proton form a bound state, then why is there no bound state for two neutrons? What information does this provide on the nucleon-nucleon force? Read this question carefully. That we are saying that nuclear force is not dependent upon charge. ठीक है? We will not have a proton-proton bound state. मान लेते हैं कि जो भी न्यूक्लियर फोर्स होगा, मान लेते हैं कि वो रिपल्शन के कंपैरिजन में उतना पावरफुल नहीं है. सो पीपीपी हमको बाउंड स्टेट नहीं मिल रहा है. ओके, बट एनपी हमको मिल जा रहा है. वी हैव एनपी, चार्ज डिपेंडेंस नहीं है. बट व्हाई डू वी नॉट हैव समथिंग कॉल्ड डाई न्यूट्रॉनिक स्ट्रक्चर? जैसे ड्यूटेरियम जो है दैट इज वन न्यूट्रॉन एंड वन प्रोटॉन, एंड ड्यूटेरॉन, जो ड्यूटेरियम है वो, सॉरी, जो ड्यूटेरॉन है दैट इज स्टेबल. Deuteron has one proton and one neutron. That is perfectly stable. It's not even a radioactive nucleus. It's a perfectly stable nucleus, which comprises of one neutron and one proton. So why can't we have a nucleus of just one neutron and two neutrons? How will you answer that? It's a, sorry? आंसर इसका जो है पॉली एक्सक्लूजन प्रिंसिपल है, राइट? तो लेट मी एक्सप्लेन ऑल ऑफ दैट. ये पूरा फिजिकल आर्ग्यूमेंट है, ये इसमें कोई मैथमेटिक्स नहीं है, ये आप फिजिकल आर्ग्यूमेंट है जो आपको स्टेप बाय स्टेप आपको लिखना पड़ेगा. पहले तो आप बताओगे दैट यस वी डू फाइंड अ एनपी स्ट्रक्चर एंड दैट एनपी स्ट्रक्चर इज ड्यूटेरॉन. ये हमको दिखता है. अब एज पर पॉली एक्सक्लूजन प्रिंसिपल, in one quantum state, I cannot have more than two particles. In fact, even if I do have two particles, even then, the most stable state, if it is only single particle, for example, if it is only neutron or only proton, then one will be spin up, another will be spin down. ये पढ़ा हमने. तो एक अगर हम spin को भी include कर लें, तो एक quantum state में सिर्फ एक ही particle रह सकता है. Okay? If I take neutron and proton, अब जब आप ड्यूटेरॉन देखोगे तो ऐसे दिखेगा कि न्यूट्रॉन का स्पिन जो है 1/2 है, प्रोटॉन का स्पिन जो है वो 1/2 है. सो सॉरी, लेट मी राइट इट प्रॉपर्ली. जो प्रोटॉन का स्पिन है वो है आपका 1/2 एंड न्यूट्रॉन का जो स्पिन है वो है 1/2. तो अगर आप ड्यूटेरॉन देखोगे तो ड्यूटेरॉन में कितनी पॉसिबिलिटीज हैं? इफ आई हैव अ ड्यूटेरॉन which is made of one proton and one neutron, then how many possibilities are there? S can be what? S can be 0, S can be 1. -1 को मैंने 1 में include कर लिया है. That I can have a singlet state or I can have a triplet state. You'll hardly find S is equal to 0 state. You'll hardly find that S is equal to 0 state. Most of the time it is S is equal to 1 state, right? If I have a neutron and neutron, then if this neutron is half, then this is going to be -half. So यहाँ पे एक ही possibility है, that is S is equal to 0. Okay, now here is the crucial part. That जो हमारा nuclear force है, that actually chooses a particular type of spin orientation. That for few spin orientation, the potential of nuclear force is much more compared to nuclear force का potential for, if let's say for example if you have spin pairing in this manner. So as a result, even though theoretically it is possible to have a bound state of two neutron, practically we do not find that because इसका जो binding energy है वो बहुत ही कम है. But in case of neutron and proton, such as deuteron, even though it was possible to have 0, but we do not find that, we find S is equal to 1. जो कि वहाँ पे पॉसिबल है. एंड उस केस में अगर आप बाइंडिंग एनर्जी निकालोगे ड्यूटेरॉन का, दैट कम्स आउट टू बी अबाउट 2.2 to 5 mega electron volt, which is a good binding energy. So that tells you that जो न्यूक्लियन फोर्स है that chooses certain type of spin preference. So it is a spin dependent force. It does not choose all type of spin. So that tells you two things. It is charge independent because it is happening between neutron and proton, but it also tells you that it is a spin dependent force, right? So theoretically, even though S is equal to 0 is allowed, practically we do not find that much in case of deuteron. And उसका कारण ये है that जो potential of nuclear force है for S is equal to 1 is much more than potential is equal to S is equal to 0. But वो न्यूट्रॉन प्रोटॉन में फिर भी पॉसिबल है, बट ये न्यूट्रॉन न्यूट्रॉन में बिल्कुल ही पॉसिबल नहीं है. तो ये हमारा लाइन ऑफ आर्गुमेंटेशन होगा, एंड उसी लाइन ऑफ आर्गुमेंटेशन के आगे हम लिखेंगे दैट ऑल्सो टेल्स अस दैट जो न्यूक्लियर फोर्स है वो स्पिन डिपेंडेंट फोर्स है, चार्ज डिपेंडेंट नहीं है. एंड आप ये भी बोल सकते हो कि स्पिन डिपेंडेंस अगर है एंड स्पिन डिपेंड्स अपॉन स्पेशल ओरिएंटेशन. सो अगर आप इसी आर्गुमेंट को थोड़ा सा और अगर बढ़ाओगे तो आप बोल सकते हो कि बिकॉज स्पिन डिपेंड्स अपॉन स्पेशल ओरिएंटेशन, इट मीन्स दैट न्यूक्लियर फोर्स इज ऑल्सो नॉन सेंट्रल फोर्स. सेंट्रल फोर्स क्या था? दैट आई ओनली हैव आर डिपेंडेंस, बट आई डू नो फॉर अ फैक्ट दैट स्पिन कैन बी डिपेंडेंट अपॉन थीटा एंड फाई. So if I have theta and phi involvement, it means that my nuclear force is a non-central force. It is not a central force. All of that inference can be made into that particular question, right? So ये argument एक एक करके आपको देना पड़ेगा, तब जाके आप आगे बढ़ोगे. अगला क्वेश्चन बहुत सिंपल है. दिस इज अ स्टैंडर्ड क्वेश्चन which should make every candidate very happy. What do you understand by nuclear forces? Explain Meson theory of exchange forces. And उसका अगला क्वेश्चन भी बहुत सिंपल है. This is a simple application of Heisenberg principle of uncertainty, right? So let's look at both of these questions together. Nucleons in nucleus is bound by a potential due to nucleons themselves, and that force due to that potential field we are calling it strong nuclear force. And we do know certain properties of strong nuclear force. It is a short range force, attractive force with a repulsive core. So around 1-2 femtometer it will be attractive, but about 0.5 femtometer it is going to be very repulsive. It is charge independent, but it is spin dependent, and it is a non-central force. So apart from R, it also depends upon theta and phi. अब यूकावा का जो मेजॉन थ्योरी है, जो क्लास के शुरू में हम डिस्कस कर रहे थे, हिज थ्योरी, इवन दो इट इज नॉट नाउ अ फंडामेंटल थ्योरी, वी हैव मोर फंडामेंटल थ्योरी विच इमर्जेस इन व्हाट इज कॉल्ड क्वांटम फील्ड थ्योरी, बट व्हाट यूकावा postulated that each nucleon is surrounded by a meson field, and as a result they continuously emit and absorb particles called mesons, pi mesons to be more specific, and this exchange gives rise to strong nuclear force. Yes, this is fine. But I will repeat this, that now we know that this exchange theory occurs at much more fundamental scale between quarks themselves. And उसका जो residual effect है, उसको हम बोल सकते हैं that is a pi meson exchange. और यूकावा ने जो पूरा potential दिया, given the fact, अब देखो ये कितना genius है ये यूकावा potential, कि ये जो potential है, this varies E minus R by R divided by R. Okay. Why this potential? If I have R very small, very small, then ये जो value है, remember exponential term minus, and if it is less than 1, it is going to be much more bigger. तो इसका जो contribution है, वो उतना ज़्यादा होगा नहीं होगा. As long as this R is less than this capital R, whatever that capital R is, we have to calculate. As long as that R is less than capital R, this term will give much more input compared to that denominator. But the moment that R keeps on increasing, तो ये term तो बड़ा होगा ही होगा, ये further reduce होगा divided by this denominator. So this potential fulfills that requirement that at very short level there is a very attractive force, but the force suddenly dissipates and comes down to 0 the moment your R increases a little bit. So this potential takes care of that. So it's not like that Coulomb potential, which is k by r, or gravitational potential minus k by r. There is a exponential term here. It goes without saying that this is not correct, because remember here also there is only r dependence. There is no theta or phi dependence, and now we know of course that it is not correct. But ठीक है, it's a good approximation. If you plot Yukawa potential, it will look something like this. But because we also have to account for repulsive potential, that when r is very less, it must be repulsive. तो ये भी हम लिखेंगे that less than 0.5 femtometer and the potential is k times r. All of these are approximations, these are not exact values, but these approximations can justify your experimental data, right? And फिर मेजॉन एक्सचेंज का आइडियली जो बढ़िया आंसर होगा वो फाइनमैन डायग्राम बनाएगा. फाइनमैन डायग्राम कैसे बनाया जाता है, ऑल्दो आपके सिलेबस में है नहीं, बट फाइनमैन डायग्राम फिर भी कुछ कुछ क्वेश्चंस में तो बना के आना चाहिए. पार्टिकल फिजिक्स का जो आपका इंटरैक्शन देना हो, क्वार्क इंटरैक्शन, वहाँ पे हमको फाइनमैन डायग्राम बनाना चाहिए. पाई मेजॉन में जो है हमारा फाइनमैन डायग्राम हमको बनाना चाहिए. तो ये फाइनमैन डायग्राम बना के आओ, फॉर्मूला लिखो, एंड ये आपका कंप्लीट हो गया. और लास्ट में बस हमने एक लाइन ऐड कर दिया है that जो Yukawa interaction है, this is used in standard model to describe the coupling between Higgs field and massless quarks and leptons. So we do find that this actually became the inspiration behind overall development of fundamental interactions at the level of quarks, leptons and gluons. अगला क्वेश्चन बहुत सिंपल है. Let me show you the question again. Ground state of deuteron, prove that radius of nucleus is this much. तो उसके लिए हमको एक वैल्यू हमको याद रखना पड़ेगा. ग्राउंड स्टेट ऑफ ड्यूटेरॉन के लिए आई नीड टू रिमेंबर बाइंडिंग एनर्जी दैट 2.225 मेगा इलेक्ट्रॉन वोल्ट. सो आई सिंपली यूज kinetic energy will be p square by 2 mu. Why I am using mu? Because it's a neutron proton system. It's a 2 mass system. So for 2 mass system I am using the concept of reduced mass. Reduced mass क्या था? m1 m2 divided by m1 plus m2. And we do know that if m1 and m2 are equal, then reduced mass becomes m by 2. I mentioned all of that. Anyways, uncertainty principle, del p into del r should be approximately equal to h cross. Del p is h cross by r, so that should be equal to about p, and kinetic energy is nothing but h cross square by 2 mu r square, p square by 2 me. So p मेरा ये है h cross by r square, so kinetic energy is h cross by 2 mu r square. And my mu, what is that? My mu is approximately mp by 2 और mn by 2, कुछ भी हम ले सकते थे. mp mn करीब करीब सेम ही है. मास ऑफ प्रोटॉन, मास ऑफ न्यूट्रॉन सेम है. अब जो काइनेटिक एनर्जी है दैट शुड बी बाउंड एनर्जी फॉर द बाउंड स्टेट, एंड बाउंड एनर्जी हमको पता है 2.225 मेगा इलेक्ट्रॉन वोल्ट, h क्रॉस स्क्वायर बाय 2 म्यू r स्क्वायर. आप ये सब कुछ करो, सिंपल सा अरिथमेटिक है. यू गेट 4.3 फेम्टोमीटर. क्वेश्चन में आपको दिखाना है कि 2.15 है. आप करके देख लेना, दिस विल कम आउट टू बी 4.3 फेम्टोमीटर. बट रिमेंबर क्वेश्चन में पूछा क्या है? क्वेश्चन में पूछा है रेडियस ऑफ न्यूक्लियन. रेडियस ऑफ न्यूक्लियाई नहीं पूछा है, रेडियस ऑफ न्यूक्लियन पूछा है. सो इफ आई एज्यूम दैट न्यूक्लियस इज, एंड एज्यूम करने की जरूरत भी नहीं है, that it comprises of the nucleus of deuteron comprises of 1 neutron and 1 proton, and I have just calculated the radius of nucleus. So radius of 1 nucleon, if I estimate the size, then it is nothing but half of that, and it is 2.15 femtometer. तो ये हमको आर्ग्यूमेंट देना पड़ेगा, एंड वहाँ से हमको आंसर आ गया. बट दिस इज अ वेरी वेरी इजी क्वेश्चन, ये आराम से कर सकते हैं. ओके, दिस इज अ गुड क्वेश्चन फ्रॉम शेल मॉडल. शेल मॉडल पे पहले बड़े आसान क्वेश्चन आते थे, अब थोड़ा सा यूपीएससी घुमा के पूछती है. शो दैट फॉर स्पेसिफिक वैल्यू एन एल there exists a large degeneracy relative to energy characterized by quantum number capital N. Find the shell closures and the magic numbers predicted by harmonic oscillator potential. तो ये जो है NL है, ये हार्मोनिक पोटेंशियल लेके ही यूज करोगे. अब ये क्वेश्चन थोड़ा सा मुश्किल देखो इसलिए है बिकॉज आपने क्वांटम मैकेनिक्स में हार्मोनिक पोटेंशियल पढ़ा है, बट यू हैव लर्नड हाफ kx स्क्वायर, यू हैव नॉट लर्नड हाफ kr स्क्वायर, राइट. When you solve half kr², अब अच्छी बात यहाँ पे बस ये है that I don't think UPSC will ask you to solve the spherical harmonic potential. ये UPSC कभी नहीं पूछेगी. But what you should know, ये आपको याद रखना पड़ेगा. इतना भी complicated calculation नहीं है, but we should know that while for simple harmonic oscillator, what was the potential? Small n plus 1 by 2 h cross omega. याद है आपको quantum mechanics में? यहाँ पे जब आप solve करोगे, you'll find that energy is n capital N plus 3 by 2 h cross omega, but that n depends upon two other quantum numbers, small n and L, where small n also will be positive, including 0, L also will be positive including 0. तो ये आपको याद रखना पड़ेगा that when you solve that spherical harmonic potential, where U is equal to half kr², then this is the energy level you are going to get, 2n plus L. अब आपको दिखाना है कि for given L, the degeneracy is going to be very very high. तो यहाँ पे हम simple सा idea use करेंगे. For a given n, there are multiple combinations of n and L. Also for each orbital angular momentum L, we can think of sub levels 2L plus 1 magnetic moments, right? And आप इसको sum करो, sigma करो, that comes out to be, आप एक simple सा summation है, इस sum को आप solve करोगे, you will find that the degeneracy level is going to be n plus 1 into n plus 2 divided by 2. But if I include the fact that in every state I can have 2, spin अलग अलग होगा, एक spin up होगा, एक spin down होगा, so multiply that with 2, and that is my total degeneracy n plus 1, n plus 2. So even if I have, let's say for example, n is equal to 2 here, then this value becomes 2 plus 1 and 2 plus 2, this becomes 12. So that tells you that you have high degeneracy level. And अब हमको shell closure में देखना है, तो हम अलग अलग values देखेंगे. That when I have n is equal to 0, what are the possible combinations? N is equal to 0, L is equal to 0, 1s, यही तो होता है, n is equal to 0, L is equal to 0 क्या होता है? 1s, energy, ठीक है, energy नहीं भी लिखा तो कोई फर्क नहीं पड़ता. But look at n is equal to 1. The possible combination that is only possible when n is equal to 0 and L is equal to 1. So that becomes 1p. Okay. How many states in L is equal to 0? Only 2. L is equal to 1, 2 into 1 plus 1. Right? So ये हम करते रहेंगे. N is equal to 2. That is now possible when n is equal to 1, L is equal to 0. But it is also possible when n is equal to 0, L is equal to 2. This becomes 2s, this becomes 1d. Why this calculation is very very important? अभी clear हो जाएगा. आप same करो n is equal to 3 पे. This is again 2 possibility. N is equal to 1, L is equal to 1. Or n is equal to 0, L is equal to 3. This becomes 2p, this becomes 1f. And एक और करके देख लेते हैं. N4, there are 3 possibilities now for n is equal to 4. N is equal to 1, L is equal to 2, n is equal to 2, L is equal to 0, n is equal to 0, L is equal to 4, 2d, 3s, 1g. अब ये पूरा आप कैलकुलेट करके देख लो. अब ये जैसे जैसे अगर फिल होगा, if I assume harmonic oscillator, I had 1s, 1s में how many nucleons? 2. 1p, L is equal to 1 here, right? So 2 into 1 plus 1, include for the degeneracy, include for the spin, I have 6. 2s and 1d, I have 12. 2p and 1f, I have 20. 3s, 2d, 1g, include all of that, you are going to have 30. So now look at the cumulative impact. 2 plus 6, 8. 8 plus 12, 20. 20 plus 20, 40. 40 plus 30, 70. So if I assume my spherical harmonic potential, then what we are looking at that ये जो numbers हैं, यहाँ पे हमारा जो सारा quantum state होगा completely filled होगा. And these are going to be the stable states, the so-called magic numbers which emerge inside nuclei. However, the actual magic numbers जो हैं, ये 2, 8, 20 तक तो ठीक है, but इसके बाद आपके जो actual magic numbers हैं वो बिल्कुल ही अलग हैं. So that tells you that ये जो पूरा मेरा assumption था that it is a spherical potential वो गलत था. राइट. एंड उसमें दो चीज़ें हमको करेक्ट करनी पड़ेंगी. एक तो पहले पूरा प्रॉब्लम ये है दैट इट कैन नेवर स्केप, देयर इज अ इनफाइनाइट बाउंड. एंड सेकंड ये है दैट देयर इज अ समथिंग कॉल्ड स्पिन ऑर्बिट कपलिंग व्हिच वी हैव टू थिंक, व्हिच वी हैव टू इंक्लूड. एंड व्हेन वी इंक्लूड दैट स्पिन ऑर्बिट कपलिंग एंड देन द मैजिक नंबर्स एंड द एक्चुअल एक्सपेरिमेंटल डेटा दैट मैचेस परफेक्टली वेल. तो ये स्टार्टिंग पॉइंट ऑफ शेल मॉडल. रिमेंबर दिस इज स्टार्टिंग पॉइंट ऑफ शेल मॉडल. इसके बाद आप पढ़ते हो when you include that spin orbit coupling, and then you see that how degeneracy further occurs between, let's say, 2s and 1d, 2p and 1f, or 3s, 2d and 1g, that you have more and more degeneracy, and how this series progresses and you come across magic number of nuclei. Last two tutorials. This is very easy. ये आपने 11-12 में भी पढ़ा है. ऐसा क्वेश्चन है, व्हाट इज द एज ऑफ फॉसिल दैट कंटेन्स 6 ग्राम ऑफ कार्बन 14C हैज अ डिके रेट ऑफ 27 डिकेज पर मिनट. तो डिके रेट से आप अभी कार्बन 14 का क्या नंबर है वो निकाल सकते हो. स्टैंडर्ड कार्बन 14 कार्बन 12 का क्या रेशियो है वो दे रखा है, एंड उससे आपको निकाल हाफ लाइफ दे रखा है, आपको निकालना है कि कितना एज का भी फॉसिल है. एंड द सेकेंड क्वेश्चन इज व्हाट वी आर डिस्कसिंग अर्लियर, resonance absorption of gamma rays, and describe the working and applications of Moss-Bauer spectrometer. तो radioactive decay ये होता है, this is the rule, n is equal to n0 e raised to power minus lambda t. अगर आपको एक नंबर ज़्यादा चाहिए तो आप कार्बन डेटिंग का जो पूरा हमारा एजम्पशन है उसको आप लिख सकते हो. नहीं भी लिखते तब भी सही होता, कोई ऐसे नहीं है, बट आई एम वेरी श्योर कि अगर आप ये लिखोगे एजम्पशन तो 0.5 मार्क्स आपको और एक नंबर ज़्यादा मिलेगा. तो कार्बन डेटिंग फंक्शंस, बिकॉज हम ये एज्यूम करते हैं कि जो कार्बन 14 एंड कार्बन 12 का रेशियो है दैट डज नॉट चेंज, एंड बिकॉज वी ऑल आर कार्बन बेस्ड लाइफ, आवर कार्बन कम्स फ्रॉम प्लांट्स and plant carbon comes from atmosphere through photosynthesis. So the same ratio of carbon 14 and 12 is also found in plants and all other living organisms as long as you are alive. But when you die, then carbon 14 starts decaying and that ratio keeps on decreasing. And every 5,700 years that ratio becomes half and half and half and half and half. And you look at the current ratio and you calculate the age of the fossil. So ये बस इतना डिटेल में नहीं, but एक लाइन में हमने लिखा है that this ratio in atmosphere does not change and same ratio is found in living organism as long as they are alive. But anyways, अब ये क्वेश्चन में देख लो क्या दे रखा है. कार्बन 12 का मोल कितना है, 0.5 मोल है. सो नंबर ऑफ कार्बन 12 एटम्स विल बी हाफ ऑफ एवोगाड्रोस नंबर. रेशियो दे रखा है कार्बन 14-12 का, सो नंबर ऑफ कार्बन 14 एटम्स हम निकाल लेंगे उस रेशियो के हिसाब से. बट डिके लॉ के हिसाब से that decay law A is lambda n is equal to A by lambda. अब A आपको दे रखा है 27 decay per minute. तो यहाँ से हमने lambda निकाल लिया. lambda is, and lambda हमको पता है log t by half life. half life year में दे रखा है, convert that into minutes. So I have my half life, I have my lambda 2.3 into 10 to the power minus 9 per minute. Put that and वहाँ से हमको n मिल गया. Current n is equal to 27. ये current decay था, 27 divided by 2.3 10 to the power minus 9. That is my current n. And original n हमने निकाल ही लिया है. Original n we have calculated here, 3.914 multiplied by 10 to the power 11. So अब बस आपको simple सा arithmetic है. T is equal to 1 by lambda, ln n naught by n. Put all of that. ये मिनट में आएगा आपका. ये लैम्डा मिनट में था तो मिनट पर मिनट में था तो मिनट में आएगा, उसको ईयर में कन्वर्ट करो, इट विल बी अप्रॉक्सीमेटली 2900 ईयर्स. सो इट्स अ सिंपल क्वेश्चन. दिस इज अ सिंपल क्वेश्चन व्हिच यू कैन सॉल्व वेरी वेरी इजीली. नेक्स्ट इज लॉट ऑफ बस थ्योरेटिकल डिस्क्रिप्शन है दैट न्यूक्लियर रेजोनेंस एब्जॉर्प्शन रिफर्स टू एब्जॉर्प्शन ऑफ गामा रेज बाय अ न्यूक्लियस व्हेन द एनर्जी ऑफ इनकमिंग गामा फोटोन एग्जैक्टली मैचेस the energy difference between two nuclear energy level. The same idea when we talk about quantization of atomic energy, the same idea quantization of nuclear energy. The challenge is recoil of nucleus. Recoil of nucleus का एक effect है. So Moss-Bauer effect में हम क्या करेंगे? There are certain solid crystals जहाँ पे जो nucleus है बहुत embedded है एंड उसका जो रिक्वायल है करीब करीब 0 है, एंड दिस इज कॉल्ड Moss-Bohr effect. And use Moss-Bohr effect. This is my diagram. You have a Moss-Bohr drive, you have a source of gamma, you have a collimator, you have a sample, and then you have a detector. And to all of that, you find certain type of resonance, absorption frequency, and based on that, you can use it to know more about nucleus, oxidation state in iron, hyperfine interaction, ion-bearing minerals, isomeric shift in chemical bonding, all of that. These are the explanation or utility of Moss-Bohr spectrum. ये आपको याद रखना पड़ेगा. इसका simple सा एक, जब भी आप Moss-Bohr पढ़ोगे, there is certain set of applications you have to remember. Okay, next question is very simple. Another question which should make you very happy because ये 15 नंबर का क्वेश्चन है, and बहुत ही easy question है. A neutron and a proton can undergo radiative capture. Deuteron है, D here is deuteron, and a gamma has been emitted. Find the energy of photon emitted in this capture. Is the coil of deuteron important? ठीक है, first 15 marker question. Second, another very simple easy question. What do you understand by critical size of reactor? Explain the main features of a nuclear reactor. Okay, this is, ये सारा डेटा आपको याद रखने की जरूरत नहीं है. रिमेंबर क्वेश्चन पेपर में सब डेटा दिया रहता है फ्रंट पेज पे, तो सारा डेटा यूज करो. n+p d+ गामा दे रखा है. मास ऑफ न्यूट्रॉन पता है हमको, मास ऑफ प्रोटॉन पता है, देयर इज अ डिफरेंस. मास ऑफ ड्यूटेरॉन भी पता है हमको, ये भी दे रखा होगा आपको क्वेश्चन पेपर में. पुट ऑल ऑफ दैट. हमारा जो डेल्टा m है mp + mn - md, ये है 2.224 MeV c². अगर हम कुछ भी रिक्वायल नहीं कंसिडर करें, लेट्स एज्यूम दैट देयर इज नो रिक्वायल, सो माय ई गामा इज गोइंग टू बी 2.224 MeV. दिस इज गोइंग टू बी द एनर्जी ऑफ दैट गामा विच हैज बीन रिलीज्ड. बट वी डू नो दैट इफ गामा हैज बीन इमिटेड देन देयर शुड बी सम recoil. So if I do my calculation in the frame of nucleus itself, where it was at rest, so when gamma was emitted, it is going to have a recoil. I make an assumption that my nucleus is very heavy. तो जो मेरा momentum है, momentum of PD should be equal to momentum of gamma, at least in magnitude. Like the actual equation should be vector PD plus vector P gamma is 0, but in magnitude it is going to be same, and that is E gamma by C. आप recoil kinetic energy calculate करो. अच्छा, by the way, I have not assumed relativistic effect, and आप आराम से prove कर सकते हो. Even if you do this much more complicated, use relativistic effect, assume that V is very high, but you will realize that no, V is not very high, and I never had to assume relativistic effect. So same question, even if you do relativistic effect, you will find that the recoil energy is about 1.3 kilo electron volt, which is very less. Gamma energy is much more. तो जो ड्यूटेरॉन का जो रिक्वायल एनर्जी है वो बहुत ही स्मॉल है, और उसको हम नेग्लेक्ट कर सकते हैं. तो बहुत ही सिंपल स्ट्रेट फॉरवर्ड क्वेश्चन है, इजी सॉल्यूशन है इसका. अगला क्वेश्चन, क्रिटिकल साइज. क्रिटिकल का मीनिंग ये होता है दैट पहले तो हमको न्यूट्रॉन को कंट्रोल करना है. फॉर दैट वी हैव कंट्रोल रॉड. बट अगर हम न्यूट्रॉन जो रिलीज हो रहा है, सो लेट्स डिफाइन अ पैरामीटर k, which is neutrons produced by neutrons lost. Nuclear fission, we know, always produces more number of neutrons than what we started with. So let's define a parameter k, neutrons produced after fission versus what we started with. So if that k is less than 1, then it means that more and more neutrons are being absorbed, and as a result my fission is not going to continue. It will not become a chain reaction and fission will stop. If my k is more than 1, then that is called supercritical, and at worst that reaction can grow exponentially, and if not controlled on the right time, it can lead to reactor meltdown, right? So critical is when reaction sustains. That reaction कुछ भी हमको करने की जरूरत नहीं है. Once it becomes critical, reaction continues as a chain reaction, but in a controlled manner. मैं लिखूंगा ये, that sustain fission in a controlled manner. This is called fission. बाकी तो बहुत आसान है. मेन फीचर्स क्या हैं? फ्यूल है, फ्यूल शुड बी अ गुड फिसाइल मेटेरियल. यहाँ पे बस आपको एग्जांपल लिखने पड़ेंगे हर जगह पे. Fuel should be a good fissile material. Moderator है, that should be water, heavy water. बहुत ही खराब डायग्राम है. I'm really sorry for this diagram, but ideally I would hope that you would make a better diagram than what I have made. आप इसमें और चाहो तो आगे बना सकते हो, टर्बाइन वगैरह बना सकते हो स्टीम के आगे, and वहाँ को इलेक्ट्रिसिटी लाइन वगैरह भी बना सकते हो if you want that, right? So this is a typical example of pressurized water reactor or pressurized heavy water reactor. ये कंट्रोल रॉड्स हैं, ये फ्यूल रॉड है. तो ये सारी चीज़ हम लिखेंगे, सबका एग्जाम्पल देते रहेंगे. खत्म है. तो दिस इज़ अ वेरी इजी क्वेश्चन. You can easily get 10 marks out of 15 if you make a good diagram and just write down examples of the important components of reactor. But ये जो theme है न्यूक्लियर रिएक्टर वाला, यूपीएससी बहुत कम बार पिक करती है. अब as it happened, they picked this theme in 2024. The last tutorial, this includes question of particle physics. पार्टिकल फिजिक्स में आपको बहुत सारा प्रैक्टिस करना पड़ेगा. द रीज़न आई एम टेलिंग यू, जैसे आप ये क्वेश्चन देखो, हर रिएक्शन में आपको लिखना है नेम द इंटरैक्शन वाया विच द अबव न्यूक्लियर डिके अकर्स, एंड हर क्वेश्चन सिर्फ 1 मार्क्स का है. इफ यू स्टार्ट डूइंग ऑल कंजर्वेशन लॉज इन ऑल ऑफ दिस रिएक्शंस, it will not just occupy a lot of space but also will take a lot of time, and you should not have to spend a lot of time. तो प्रैक्टिस करने का फ़ायदा क्या होगा कि आप इंट्यूटिवली देखोगे कि अच्छा ये क्या हो रहा है यहाँ पे, कौन सा, अगर मान लो सारा कंजर्वेशन लॉ अगर कोई वायलेट हो भी रहा है तो इमीडिएटली दिखेगा. यू विल ऑल्सो फाइंड दैट इफ leptons आर इन्वॉल्व्ड, quarks आर इन्वॉल्व्ड, then it should be weak interaction. If you have photons are involved, it should be strong interaction. तो ये चीज़ें ना देखते ही चमकना चाहिए, that कौन से किसको चेक करना है to give this final confirmation that strangeness is not conserved, it's a weak interaction. तो ये चमकना चाहिए that what is not conserved here. And ये आप सब में सारे conservation laws अगर अप्लाई करोगे, 1 नंबर का क्वेश्चन है, lot of space, lot of time, don't do that. Okay. So anyways, but first let's start with simple question. This is a question. Explain why each of the following particles cannot exist according to Quark model. A baryon of spin 1, anti-baryon of electric charge 2. Baryon is made of 3 quarks. सबसे बढ़िया एग्जाम्पल ऑफ बेरियन जो है प्रोटॉन एंड न्यूट्रॉन ही है, मेड ऑफ 3 क्वार्क्स. एंड 3 क्वार्क्स मीन्स क्वार्क्स आर फर्मियंस. फर्मियंस का जो स्पिन है हाफ है. So if I have 3 quarks, then there are only 2 possibilities. The 2 of them align, so that cancels out, and the third one remains 1 by 2. Or all 3 of them are aligned, then it is 3 by 2. So there is no possibility of having 1 as a baryon. So S is equal to 1 is forbidden in Quark model. Charge पूछा है कि UDS. So anti-baryon is made of anti-up quark, anti-down quark. And we do know that the maximum positive charge anti-quark can have is plus 1 by 3. Negative charge minus 2 by 3. So maximum possible positive charge is plus 1. So I cannot have plus 2 charge for a anti-baryon. Simple. So this is a very, I just need to remember what type of particle baryons are. Next question क्या है? ये सारे रिएक्शंस दे रखे हैं, आपको बताना है कि कौन से इसमें पॉसिबल हैं, एंड जो पॉसिबल हैं इफ फॉरबिडन स्टेट विच कंजर्वेशन लॉ इट्स अकरेंस वुड वायलेट, राइट. तो पहला तो देखो ये बेरियन नंबर दिस शुड बी वेरी क्लियर कि बीटा डिके है. दिस इज नथिंग बट बीटा डिके. बेरियन नंबर इज कंजर्व, लेप्टॉन नंबर इज कंजर्व, चार्ज डेफिनेटली कंजर्व्ड, एनर्जी मोमेंटम तो ठीक है वो मान सकते हैं कंजर्व्ड है. So this is allowed, and we can also write, because this is very famous, we can write that this is parity is violated, and this is an example of beta decay. अगला क्वेश्चन देखो. You have lambda and then you have pi mesons, but lambda is a baryon, pi mesons are not baryons, so baryon number is violated. So I immediately jump to the charge is not violated. 0, 0, charge is not violated. Right, so I immediately directly jump to the main part. Similarly, look at here, pi meson, spin is 0, यहाँ पे photon and electron है. Electron has half spin, again forbidden, spin is not going to allow that. Now this is a big reaction. Pi meson, E minus, E plus, neutrino, antineutrino. I do think that they should be allowed, and involvement of neutrino means that it should involve via weak interaction. आप एक बार देख लेना, I'm going to get this solution uploaded. Check कर लेना if it is wrong. But I do think I looked at the quantum numbers and it should be allowed. E minus, E plus, mu plus, यहाँ पे भी बहुत सारी चीज़ें करीब करीब conserved हैं. Even spin, remember, spin is 1 by 2, 1 by 2, 1 by 2, 1 by 2. So that combination, there is a combination possible where I can have 0 as a possibility. So it's possible there is something called phase space, and in phase space this possibility is going to be very, very less. So you do not find such type of interactions. अब ये क्वेश्चन है जो 10 क्वेश्चन थे. अब यहाँ पे देखो डायरेक्टली ये दिखना चाहिए कि वीक इंटरैक्शन है, स्ट्रेंजनेस इज बीइंग वायलेटेड, दैट इज गोइंग टू बी वीक इंटरैक्शन. So this is what I was saying. I directly jump. The more I practice, I realize I immediately can jump to the main point. यहाँ पे बेरियो नंबर कंजर्व नहीं है तो रिएक्शन जो है अलाउड ही नहीं होगा. All particles compatible to strong interaction. यहाँ पे फोटोन निकल रहा है. I will mention this is electromagnetic interaction. So I do not have to go into all sort of conservation, those 12 conservation laws which you remember, and you try to see that. That is going to be very lengthy process, right? So this, by the way, this is very interesting. Electron positron annihilation, and such type of annihilation occurs only and only because of electromagnetic interaction. Again, release of photon further confirms that this is going to be electromagnetic interaction. Okay, this is a beautiful question जो syllabus दे रखा है आपका, physics of neutrinos. एक syllabus में है आपके physics of neutrinos. So last 3 questions of the discussion, today's discussion. How could you establish that neutrinos and antineutrinos are 2 different particles? Okay. This is a very standard question. What is meant by strength of interactions of elementary particles? Classify the different forces on the basis of this strength of interaction. And third is again a very similar question. What are the various conservation laws? And based on that आपको ये देखना है कि ये allowed है या नहीं है. कैसे करते हैं न्यूट्रिनो एंटीन्यूट्रिनो को डिस्टिंग्विश? 2 factors, 2 things. First is lepton number and second is helicity. So helicity as a concept was defined for neutrino, right? ये parity violation in beta decay जब आप पढ़ोगे तब helicity के बारे में आप पढ़ोगे वहाँ पे. So anyways, पहले तो आप lepton number हम देखेंगे. That look at these 2 different reactions. I have antineutrino plus proton, neutrons plus positron, that positive beta decay, versus neutron plus antineutrino plus neutron, proton plus electron, that beta minus decay. So in these 2 reactions, अगर neutrino और antineutrino अलग नहीं होते, right? So इस केस में जैसे for example देखो जो हमारा lepton number है, lepton number here is -1, here is -1. So lepton number has to be conserved. Here it is +1, here it is +1. So we already know that these 2 particles, electron and positron, they have opposite lepton number. We also know that these things P and N will not contribute here. So only thing which now has to differ, that these 2 particles should have 2 separate lepton number. तो पहला तो हमारा experimental verification ये है that lepton number conservation के हिसाब से neutrinos and antineutrinos are different with different lepton number. And the second is that they also differ in helicity. This was one of the most famous experiment after which the helicity was defined, that parity violation occurs in beta decay. And helicity is essentially spin direction to momentum. There is a specific way to define it, S dot P. And जो neutrino है, that is left-handed in helicity, and जो anti neutrino है that is right handed. That somehow weak interaction, it prefers a particular coordinate orientation, and hence parity violation occurs in case of beta decay. So you can explain that with help of this concept of helicity. So these are the two ways how we distinguish between neutrino and antineutrino: lepton number conservation and helicity. And ये बहुत easy question है. Strength of interaction का क्या मतलब है? This simply means how strongly elementary particles influence each other via fundamental force, and that determines interaction का probability क्या है, time scale of interaction क्या है, and there is a term which is called coupling constant. Coupling constant is a essentially unitless quantity which tries to measure the relative strength of fundamental forces. और ये भी दे रखा है आपको फंडामेंटल फोर्सेस के बारे में लिखना है. एक सिंपल सा टेबल बनाओ आप. रिलेटिव स्ट्रेंथ क्या होगा? स्ट्रॉन्ग फोर्स इज द हाईएस्ट, देन इलेक्ट्रोमैग्नेटिक फोर्स, देन वीक फोर्स, एंड देन ग्रेविटी. These are the mediating particles. This is the range. Gravity and electromagnetic force are infinite range forces. These two are short range forces, and which are affected by those particles. And simple सा अगर हम देखें स्ट्रेंथ के हिसाब से तो स्ट्रॉन्ग इज स्ट्रॉन्गेस्ट, ग्रेविटी इज वीकेस्ट. दैट इज व्हाट इट सिग्निफाइज, दैट डबल ग्रेटर मार्क. एंड द लास्ट क्वेश्चन ऑफ द पेपर, व्हाट आर द कंजर्वेशन लॉज? एनर्जी, मोमेंटम, इलेक्ट्रिकल चार्ज, बेरियो नंबर, लेप्टॉन नंबर. उसमें भी एल ई, एल म्यू, एल टाउ तीनों अलग कंजर्व होंगे, तीनों के लिए अलग अलग लेप्टॉन नंबर होगा. एंगुलर मोमेंटम, टाइम रिवर्सल, charge conjugation, CP, CPT. But three things, very important conservation: strangeness, charge conjugation, and parity. These are conserved in strong and electromagnetic interaction but violated in weak interaction. अगर हम isospin की बात करें, so that is violated in strong interaction. So anyways, based on आप ये देखो, pi meson plus neutron. यहाँ पे baryon number is not conserved. Neutron has a baryon number. एंड यहाँ पे देखो आप, दिस इज एंटी न्यूट्रिनो प्रोटॉन, न्यूट्रॉन प्लस इलेक्ट्रॉन. यहाँ पे चार्ज ही कंजर्व नहीं है. दिस इज +1, दैट इज -1, so this is also forbidden, right? So this is not a allowed interaction, right? So nuclear and particle physics, it requires much more time than quantum mechanics. Quantum mechanics still is easier because you have to, there are standard models, there are essentially certain type of potentials which you have standard way of deriving them. But in nuclear physics you have actual problems, that you have actual nuclei and they're exhibiting different type of properties, and now you have to develop a theory to explain those properties. So it is lot of that experiment driven theory, and as a result you will find many theories which will explain different type of different events. तो इसका जो scope है वो wide है. यूपीएससी सिलेबस के हिसाब से भी अगर आप देखोगे तो जो न्यूक्लियर फिजिक्स का स्कोप है वो वाइड है कंपेयर टू स्कोप ऑफ क्वांटम मैकेनिक्स, एंड अ टॉपिक विच शुड नॉट बी टेकन लाइटली एंड विच शुड नॉट बी इग्नोर्ड एट ऑल, राइट? एनी क्वेश्चंस, एनी डाउट इफ यू हैव? सो इफ just in case if you do have a doubt, all the best guys.
The UPSC exam doesn't defeat you with difficulty. It defeats you with confusion, lack of clarity, lack of direction, and preparation that feels scattered. At Vision IAS Delhi, we rebuild your UPSC journey with structure, strategy, and support that doesn't waver. Get complete coverage of GSC, SAT, and essays step by step, PT 365 and Mains 365, so current affairs stop feeling like chaos. Personal mentorship, not just advice, but actual strategy guidance. Test feedback loops, because growth begins where guesswork ends. Toppers didn't just prepare, they built the right foundation. Now it's your turn. This isn't just a course, it's where clarity, consistency, and confidence begin. The UPSC exam doesn't defeat you with difficulty. It defeats you with confusion, lack of clarity, lack of direction, and preparation that feels scattered. At Vision IAS Delhi, we rebuild your UPSC journey with structure, strategy, and support that doesn't waver. Get complete coverage of GSC, SAT, and essays step by step, PT 365 and Mains 365, so current affairs stop feeling like chaos. Personal mentorship, not just advice, but actual strategy guidance. Test feedback loops, because growth begins where guesswork ends. Toppers didn't just prepare, they built the right foundation. Now it's your turn. This isn't just a course, it's where clarity, consistency, and confidence begin.